Have you ever just looked at some data and had this gut feeling, that there's a pattern hiding in there, but you just can't prove it? Well, today we're diving into a really powerful statistical tool that does exactly that. It's called the chi-square test, and it's a brilliant way to find those hidden relationships and check if your theories actually line up with reality.
All right, so here's our game plan. First, we'll talk about the basic question this test is built to answer. Then, we'll get into the simple but really powerful logic behind it. After that, we're going to walk through two real-world examples, one about worker mistakes and another about, of all things, shampoo, before we wrap it all up by seeing how this test turns our hunches into actual solid evidence.
So, what's the big idea here? Look, the chi-square test isn't about just mindlessly crunching numbers. It's a tool that's designed to answer a very specific kind of question, and most importantly, to move us beyond relying on just our intuition. Think about a question like this. You could just guess, right? Maybe you think, yeah, people probably get tired and sloppy in the afternoon. But how do you really know? Is that a real significant pattern, or are the mistakes just kind of happening randomly? This is exactly the kind of spot where you need a formal test. And this brings us right to the core concept. Honestly, the magic of the entire chi-square test boils down to one simple, elegant comparison. This idea is what drives the whole process. So on one hand, you have your observed numbers. That's what you literally saw, what you went out and counted in the real world. And on the other hand, you have your expected numbers. This is what you'd predict the numbers would look like if your theory was true. For instance, the number of mistakes you'd expect to see if they were spread out perfectly evenly all day long. The test then takes those two sets of numbers, what you saw versus what you expected, and it boils that difference down into a single score. That score, that's our chi-squared statistic. And the bigger that number is, the bigger the gap between reality and your initial theory. So here's the bottom line. Is that gap big enough to actually be meaningful? Or is it so small that it could have just happened by pure chance, just random luck? This test gives us the statistical ruler we need to finally measure that difference. Okay, let's put this into practice with our first case study. This is what statisticians call a goodness of fit test. We're basically testing how well our data, the observed stuff, fits our theory about randomness. So check out the data. Over the whole day, a total of 50 defective parts were found. Now, if those mistakes were truly random, we'd expect to see a perfectly even split, 12.5 in each time slot. But that's not what was observed. Look here, only 8 in the morning, but then 16 right after lunch. Something seems to be going on. So now the test takes all those little differences we just saw and boils them down into one single number that represents the total gap between what we saw and what we expected. For this data, that chi-square value comes out to 3.28. So, the big question is that a big number? What does 3.28 even mean? Well, by itself, it means nothing. We have to compare it to a statistical cutoff value. Think of it like a high jump bar. And for this test, that bar is set at 7.815. The rule is super simple. For our pattern to be considered significant, our number has to be bigger than that cutoff. It has to clear the bar. And our value, 3.28, doesn't even come close to clearing the bar of 7.815. So even though the defects weren't perfectly even, the difference is still small enough that it could just be random noise. It looks like our initial gut feeling was wrong. We just don't have strong enough evidence to say the pattern is real. Okay, so now let's take that exact same logic and apply it to a totally different and actually more common kind of problem. We're going to test for a relationship, or what's called a test for independence. This is a classic marketing question, right? A company wants to know if two different things, in this case, income and brand preference, are somehow connected, or if they are totally independent of each other. Our starting point, our null hypothesis, is that they are independent. And this right here is one of the most useful ways you can apply the chi-square test. It lets us dig into survey data with categories like high, medium, low income, or prefer versus don't prefer, and see if there's a real statistical link between them. Okay, so here's the raw data, what was actually observed from a survey of 350 people. We can see how many people from each income group felt a certain way about the shampoo.
For example, you see 15 people in the high-income group strongly preferred it, but way over here, 66 people in the low-income group only moderately preferred it. All right, so we run the exact same process. We compare these results to what we'd expect to see if income and preference had absolutely nothing to do with each other. And when we run the test this time, whoa, the result is not small. We get a huge chi-square value, 38.763.
And this is where you get that aha moment. This brilliantly shows the power of the test. Our calculated value is a massive 38.763. The statistical cutoff value, that high jump bar for this test, is 12.592. Our number doesn't just clear the bar, it absolutely blows it out of the water.
In this case, the conclusion is crystal clear. The gap between what we saw and what we'd expect from random chance is just massive. So we can confidently reject our initial idea that they were independent. The evidence is incredibly strong. Income level and shampoo preference are definitely related. And now a marketing team can take that and run with it.
So let's just pull this all together and zoom out for a second. We've seen how this one really elegant test can be used in a couple of different ways to take us from just guessing to actually knowing.
So really, you've got two key moves with this test. First, the goodness of fit test, which checks if your data lines up with a theory, like in our defective parts example. And second, the test for independence, which checks if two different variables are connected, like in our shampoo survey.
And that's really the bottom line. This test gives us a structured way to check our gut feelings. It lets us look at data broken down into categories and figure out if the patterns we think we're seeing are real or if they're just ghosts in the noise of randomness.
And that's the thought I want to leave you with. What connections are you just assuming exist in your own work, or even in your daily life? From how customers behave to your own personal habits, a test like this gives you the power to stop guessing and to find out for sure. Thanks for watching.